Hi, I've been learning about the PIO state machines on Raspberry Pi Pico W. Um, been watching Paul McCord's great lessons on doing that, but this week he didn't give us any homework to do, so I thought I'd take what I've learned and try to make a practical use for it. So I have a one of those ultrasonic distance sensors in the kit, and I figured, well, it'd be a uh, good test for it. It's a lot of timing involved with that, so I uh, thought, well, I'll do that. And so first thing I remember, I took. I don't think Paul's done the distance sensor on the Pico W just using MicroPython yet, but um, it's I remember him doing it back in the Raspberry Pi on the regular Raspberry Pi when he was doing those lessons. And I remember that we had to do some conversions, and I uh, figured, well, that's the first thing to get out of the way is the conversions. So you need to, since it's ultrasonic, you're dealing with the speed of sound. So um, it's the speed of sound is 340 meters per second, but we are interested in centimeters per microsecond, actually. So we had to do some conversions. So as Paul taught us before, if you want to go to microseconds, you just put the 1 second is equal to a million microseconds, and then do the same thing for meters to centimeters. 1 meter is equal to 100 centimeters, and you cancel out the units, and meters and meters, and you end up with the 34,000 centimeters, and then over 1 million microseconds. So you do the reduction, and you get this part here, and it's it's uh 0.034 centimeters per microsecond. But I wanted to know how many microseconds it would take to get a centimeter. So you have to do one over that, and you come up with 29.4 microseconds for each centimeter. Of course, the sound has to travel to the object and back, so we're multiplying that by two, and you're getting about 59 uh, microseconds for each 2 centimeters of travel, but the distance is half of that, so it's about 59. And so I did that, and I said, well, next thing I think I ought to do is go to the data sheet on it. Let's see if I can find a data sheet on that. I think this is it. So here's the data sheet, and let me get myself out of the way a little bit. And when I did found a data sheet, it actually gave me a lot of the information I was interested in uh, doing on it. I remembered the timing and everything, but it gives you, I figured 59 centimeters per, I mean, microseconds per centimeter. And they're saying it's 58. So it's just a rounding error, I think, on their part, because 29.4 plus 29.4 is closer to 59 is 58. But I ended up using 58 anyhow. You could also do it for inches or whatever. But the thing is that I went to the data sheet for was basically the timing of it. You have the timing where it's low, and then you have to raise it high, and it says they want a 10 microsecond high, and then you bring it back low again, and then the sensor will send out a pulse through one of them, and then it'll wait for the echo to come back. And on the echo pin, it'll be low, and then once it's done sending that signal, it'll go high. And the length of time it's high is your number of microseconds that's taking to do the traveling. So um, you have to, after you send your pulse, you'll have to wait until it goes high. Then you'll start counting your microseconds. Then when it goes low, then that's when you do you know, send that number of microseconds back to your uh, um, your microcontroller. So, and then it does say up here, let's see, or down here. Oh, where is it? Oh, yeah, you want at least 60 milliseconds per measurement cycle. So I didn't I didn't want to just do this part up here. I didn't want to just trigger on that. So what I do is after it goes low, I'm doing 80 milliseconds. I'm trying to get like 10 10 readings per second. So I just said 80 milliseconds here, and whatever the time it took here. It's probably a little less than uh 100 milliseconds per read, but it's definitely more than 60. So that's what I that's what I was going for there. So anyhow, let's get to well, I did some pseudocode. I was thinking about how to do it, and I just said, oh, I need to write some things down. So um you can set the frequency on that, and I just said, well, it might as well just set the frequency to 1 million, which is microsecond. Each cycle will be a microsecond. And um like I said, I knew I wanted that 80 millisecond delay. And I thought about putting it at the top, and then I crossed off, and I ended up putting that at the bottom anyhow. But so we're going to trigger the pin low. The pin should already be low, but I put in this extra cycle, just other extra command, just to make sure it does that. And we went for 10 cycles, so we can put in the brackets 9 plus the one uh, for the set, and then we can do that. And then we're going to set the trigger pin high, and again for 10 cycles. And then we're going to set it back low. And here's where I've been reading about a couple different things that we haven't gone over in Paul's lessons. So they have a wait command. So I wanted for the wait for the from where it goes from low to high. The echo ping goes from low to high. So we're going to be able to just uh, block until we get that high, and then it'll continue. And then I said, well, we need to do a timing loop. So I decided that I just want to count the number of centimeters. So I have a timing loop that uh, counts 59, actually 58 um, microseconds, so 58 cycles to go through that loop and check everything. And then you're good. Um, I said check for timeout. It doesn't say so in here, but I think that, well, it says it has a 4 meter. Let's see. I'll just leave it there. 4 meter range. I think that the Arduino library stops it at 300 centimeters or 3 meters. So I decided to use the three. So I'm also, when I'm doing this timing loop and counting up how many centimeters we got, if it goes over 300, meaning it's out of range or it didn't get a signal back, then after 300, it's going to time out and not give you a reading for that pulse. And then once we get it, we're going to send the number of centimeters to the ISR, and then we can push it into the FIFO register. And Another thing I decided to do was the IRQs. I've seen a couple people use IRQs and I've done some reading on them. So I figured I'd send a IR trigger an IRQ, and that would handle the get side of the um, in your MicroPython code, so that you didn't have to keep looking for or keep trying to get or seeing if there's data to get. So by doing this I mean IRQ, we can um, trigger interrupts routine to go do that and get the data and put it into a variable, and it'll be available to the main program. Once you do that, if you make it a global variable, it's going to do that. And then we need 80 megas a millisecond, 80 millisecond delay, like I said. I had to make the readings, so that they happen about 10 times a second. So I put in the code for that. So with this in hand, I said, well, we can do that. And so we'll go to the code, I think. Let's go to the code. So this is my code. Um, I'm using time in my main program, so I needed time, and we need to import pin, and to use the PIO, you got to import the RP2 uh, library. So we got that. Like I say, this distance, that's going to be my centimeters, and you got to declare that so that you can use it in the global variables and stuff like that. And so let's look at the pins. Well, first of all, let's go. A lot of times I'm lazy when I'm coding or wiring up things. So you got the four pins on the thing. From left to right, you got uh, VCC, then you got trigger, and then you got echo, and then you got ground. And I looked on the data sheet, and this thing only draws 15 milliamps. That's just about the top range of what you're supposed to draw on the pin, each one of your GPIO pins. But I said, I think it'll handle it. So what I did was I used the ground here, and I could just plug it right into the board right on the empty row of pins I had here. So you got ground, and then this would be 21 is going to be echo, 20 is going to be trigger, and 19, I'm just setting a pin to output and making it high, and that supplies power to the sensor. So I've done that with a couple other sensors. I forget which one, the temperature sensor maybe. I can't remember, but it's always I always like doing, saving some wiring. Otherwise, you had to have a bunch of wiring on your thing. So this way you just plug it in and go. So anyhow, let's get back to the code. So again, like I said, we had 19 was going to be our power pin, so we just made that an output and put power on. 20 is going to be the trigger pin. 21 is going to be the echo pin, which is pin in. And I don't know with the PIO whether you actually need to set these pins up. Sometimes I think some of them get set up in here, but it was easier just to know what the name of the two pins were. So when I went ahead and did the setup for the PIO, and I could just use the pin numbers. So, or the names of the pins. Here is my uh, interrupts routine. So we're going to just all you're going to do, like I said, bringing in distance as a global, and I am actually starting at 300 and decrementing as I go, and then whenever the echo goes low, then I'm sending that value. So if it was 300 and it was 100, and it dropped to 200, that's going to send the 200 in. So then I take the 300 and minus the 200, and that gives you that, okay, it was 100 centimeters is where you get on that. So um, I this is the math that you do in your routine. I tried to think of a way that I could start at zero and increment up, but it just seemed like that it was going to be a whole lot more lines of code. I used 20 in my PIO program, so um, didn't have a whole lot to spare. Only had a dozen lines of code to spare anyhow. So figured this would be all right, and I can just do one math thing on here and probably not take, hardly any time at all. But this is going to happen over and over and over again, and it doesn't, your interrupt just handler just gets taken care of on a schedule, or when it reads it, it's going to stop at a convenient point. Your regular program's going to stop at a convenient point and go do this, and it's going to set the distance again. And next time you read your distance in your uh, regular program, you're going to get the amount. So you're going to get whatever the latest amount is up there. So anyhow, like I said, I only actually had to uh, trigger pin is an out, and um, you don't do anything with the input pins up here when you do the ASM dot underscore PIO. You don't have to deal with the input pins there. And so this is the um, code we're going to call when we do this. So um, it's probably one of the more complex codes I had, and there's probably an easier way of doing it, but I'm not sure whether there is or not. But anyhow, this first part here is that um, we're going to get we need to get the value of 300 in the X before we start decrementing X to find out how many um, centimeters we have. So we need to get 300 in there. Of course, you can't put that many digits. It's a uh, 5 and 4 is nine binary digits, and you can only put 5 in using the set. So I took the most significant bit, uh, 5 digits, and I'm moving them setting them to X, and then I'm moving X into ISR. And now to think about it, you might have been able to do this all in one set, might go into ISR. I can't remember. But anyhow, I took 2 lines to do that. And then uh, the next thing was you got those in there. Now I took the last 4 digits, the 1100, and I put those in X. And now you're shifting those 4 digits from X into the ISR. And then you have your binary representation of 300 in the ISR, and you just move that back to X. Now you have it ready to decrement. So that's good. And the next thing we're doing here is we're just setting the trigger pin low for 10 microseconds, setting it high for 10 microseconds, and then setting it low again. And here's where we're using that wait, and we're going to wait for the echo. The wait, you get to choose which polarity. So we're waiting for it to turn to 1, because when you do this triggering, uh, echo should be 0 when you're doing that. And so you're waiting for the 1. And what you're doing is it's the waiting is on the input pins. So down here, I had my in base as echo, which is the pin we use for echo up here. And then we have the trigger as well. And I guess I could talk about this. Like I say, I set it up ping is our one we're using. State machine 0. Our frequency is 1 million. And set the base. This is when we're setting, we need the uh, starting point for setting. That's where trigger pin is. And I'll talk about this jump pin. That's something new that I hadn't used before as well. That's set to echo as well as the in base is set to echo. So let's go back up here to the code. We're waiting for it. And when it goes from 0 to 1, then it's going to release out of this blocking wait, and it's going to go head down. And so here's what we're doing here is um, we know because it passed this that that pin is going to be high. And so this is while the echo pin is high, you're going to um, use your counter in decrement. And you notice I got 28 clock cycles here, so that's 28 plus 1 is 29. And then this is where the logic came crashing down on me. It took me a long while, but you actually have to, because you're checking two different things or doing jumps, you want to jump when as long as the pin is high, you want to jump. And also you want to be able to do a jump with a decrement in it. So I had to go down here and all the way at the bottom, all the way past the loop, it's like a section of code that's never going to get to it except for when when you call the label. So you're coming from, you're going to if the pin is high, you're going to go to decrement, but you're going to wait 28 clock cycles. So the DEC label is down here, and then we're going to uh, jump on X decrement. So as long as X is greater than 0, it's going to go back up here to CM, this label CM, and it's going to do that over and over again until it gets until it it goes low and then it's going to continue on down here, or it's going to time out where the X decrement gets to 0. Remember X started at 300, and if it goes through it 300 times and doesn't find it, then it's going to if this ends up being 0, then it's going to just fall through and continue on. And we still want it. So even if we have a bad a no read or whatever, we still want to do our delay so that we maintain at least that 60 milliseconds in between them. So we're just go up here to this do delay, and we are doing my timing. I spoke about this in the last video where you uh, fill the ISR with ones, null is 0, and you're inverting them, so it's all ones. And then you're using in and you're pushing zeros. How many you're pushing is uh, depends on how many bits you want. So I decided, well, I can push 12 bits, and then how many ever bits, and then you invert it again. So this makes your counter your Y so that you can have a bigger number in there. So um, 12 bits is 4096, and I just I knew I wanted about 80 milliseconds, so I just said, okay, 80,000 cycles, 80,000 microseconds would be uh, 80 milliseconds or 80. So I just divided by the 4,000, and you come up between 19 and 20. So I decided to use 20, and it's a little over, but it's closer to 8 milliseconds than it is if you do 19 instead. So that's where you're doing starting your timing loop and you're ending your timing loop. And when you're done, you just jump back to the top and start over after your timing, and then you start your triggering again and all that. So I probably didn't explain it very well. But anyhow, so like I said, we have this IRQ in here. Oh, I probably didn't go to that part. So when you when the jump pin, when it goes low, it's going to fall through here, and you move X to the ISR, and then you push it to the FIFO buffer. And after it's pushed in there, then you can do this, set up this IRQ, trigger the IRQ, and that will make uh, your IRQ fires. It's going to go to whatever function you have in here, which is the get, which is just going to do, it's going to do the get and it's going to put it in there. Like I said, that way you don't have to do any of the polling for the get or making sure that the get's available or whatever. So that's what we're doing there. And at that point, it's going, it's this label doesn't, it just doesn't affect it. And you're just going to the counting loop again. So after you do your reading, you put it out on the um, FIFO and then trigger your ISR so you can get it. And then you do wait a while and then you're going to go back up to loop. So, and jump to loop. Got the unconditional jump to loop up here. But anyhow, that's probably didn't explain it very well, but that's how it works, and it works pretty good actually. I don't know, I might have it running already, but I'm gonna turn it off and we'll turn it back on. And so yeah, so you your function for every time the interrupt effect happens, it's going to do this. Like I say, just wherever it is in the code, it gets an interrupt, it's going to go do this, and then it's going to go back to the code. So they are completely separate from the code. And as far as I know, they don't there's no kind of, crash scenarios where you're in the middle of doing something and you get this. It's going to find a good place to stop and go do that. So, like I said, that's going to happen all on its own. I don't, whatever I put in my code down here, regular code is not going to do anything. But all I have down here in my regular code is I'm going to sleep for half a second and print whatever the distance is and just keep doing that over and over again. So let's go ahead and get her running. All right. So you can see that it's got my hand up against it. And I did test it by pointing it at the ceiling, and I measured from the ceiling to the echo with a measuring tape, and it's about 165 and a half uh, 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 centimeters. So it's dead on as far as that. So it's working. And doesn't work with your hand in front of it. Sometimes it passes. If I use a piece of paper, it kind of just, you can get it all the way down to 3 or 4 and bring it out, back in. So all the pinging is happening in the background in the PIO, and it's not affecting the MicroPython at all. So there's, you don't have to, you only need to go find out what the distance is when you want to. You can do it, 10 times a second. You can do it 100 times a second. Whatever number's in there, it's going to come back to you, It might not change if you check in it a whole lot, it might not change doing that, but when it does change about 10 times a second, it's going to update it. And like I said, down here, all I got is I'm checking it every 500 milliseconds. So um, it could be changing in between those, but we're only worried about the distance when we worry about it. So we got that going on. So yeah, it's working just fine. Anyhow, I thought that was kind of cool to get that working, and um, it definitely was probably I, I enjoyed PIO, learning about PIO, but actually working with it, it's not enjoyable. I could have wrote this code MicroPython in about 10 minutes. I think I spent a half a day trying to get all this to work. One thing is it's hard to troubleshoot because there's no really ways of troubleshooting it. Um, just, you got to figure out what you're doing wrong. I know I forgot to do the active equals one. And I said, man, why is it not working or anything? And why is it not looking like it's working? And I spent probably a half hour trying to figure out, oh, I forgot to make it active. I had all this code in there and I said, I forgot to make it active. And you can probably see I got lots of demonstration programs of how each one of these, like the weight, I wasn't sure how that works, so I cobbled together a little program to just wait like on a blink, and then if you hold a button down, it'll pause the program until you let go of the button or whatever, and the blinking stops. Same thing with the jump. I had to figure out how that worked a little bit, but it's a learning process and certainly not my favorite thing to do on microcontrollers, but I guess it's with anything you learn as you go. Anyhow, thanks for watching and have a great day, everybody. Uh, Thanks, Paul, for teaching us about the PIO.